So yeah, welcome from my side as well. My name is Linus Scholz from the Joran Aerospace Center. And today I will give you some introduction to Boolean satisfiability-based routing of quantum circuits with Qronos. And since I assumed the audience to be quite mixed in terms of their knowledge and background knowledge and for quantum circuits, please let me give some more basic introductions so we can all work on the same foundations for the later on presentation of Qronos. So the questions today that I would like to answer are: what do gate-based quantum circuits look like, and why is circuit routing important? What are Clifford circuits? What are Boolean satisfiability problems, and how can they help? And last but not least, of course, what is Qronos? So let's start off with the first question of what is routing. Here I gave you an example of a very simple quantum circuit. In particular, this is a fan-in gate. And in this fan-in gate, you can see 10 qubits, which are represented by those horizontal lines, which are called wires. And generally, quantum circuits are executed from left to right. So the very first operation that is partaken here is this gate between the qubits D6 and A0, which here is a controlled NOT gate. And thereafter, you also have 3 further controlled NOT gates to complement this fan-in gate. And this might be some arbitrary algorithm that a quantum programmer would like to execute. And if we would now like to actually execute this algorithm on quantum hardware, there are some quantum hardwares, for example, superconducting qubits, which do not allow certain connections between qubits. So, for example, here, let's assume we have this topology of connected qubits on the quantum hardware. You can directly see that the qubits D6 and A0, which the quantum programmer would have liked to connect in his algorithm, do not connect to each other and therefore cannot directly talk to each other. However, they are still connected in terms of connections mitigated by other qubits, which could be used instead. And the process of routing here becomes quite important, since this is for certain topologies for certain architectures of quantum computers, the standard case that has to be applied. And if you would now like to execute still this circuit on that hardware, you would have to rewrite this quantum circuit to match the topology of the respective quantum hardware. And this is precisely what quantum routing is about: to rewrite this quantum circuit so that it can match the topology here. As you can see here, the resulting circuit of the now compiled quantum circuit looks like this. You only have gates that are multi-qubit gates, which connect now those qubits on the hardware which are actually adjacent to each other. So for instance, here, the qubit A0 and A1 that are used here are actually directly connected here. You then have a connection between A1 and D2, which is connected also in this multi-qubit gate. And last but not least, you also have the connection of D2 to D6, which again then is mitigated here. And therefore, this is the problem of routing is not only a compiling process to the hardware, it's furthermore also an optimization problem, since you can in principle add multiple gates in between to still represent the exact same functionality of your algorithm. Yet the longer the circuit becomes, the lower the fidelity of the quantum circuit will be, and the higher the error that your final result that you measure will have. And you would therefore also find the shortest circuit possible that still represents the functionality of your algorithm on the desired limited hardware. Therefore, circuit routing also is a circuit optimization problem. And this problem is tackled in our program by using a so-called tableau representation of Clifford circuits. I will go into detail a bit in a moment. And this is encoded in terms of a so-called Boolean satisfiability problem in conjunction with a binary search, which I will also like to explain in a moment. Challenges here are, first of all, the complexity of the problem. So this is anything but trivial, how to encode this type of problem, and also the mechanics underlying therein as well. And not also this, but also to make this encoding itself efficient. It doesn't help you if you can find a solution, but it takes years due to a bad encoding. You would also like to find the best encoding of your problem to make it solve and compile as fast as possible. Even more so, this shall only be one feature of the future program to be that can be addressed. So we would also make this modular and flexible to be combinable with other strategies of circuit routing and optimization. And last but not least, from a personal side of view, I would also make the program user-friendly so that even the less experienced quantum programmers can use Qronos without all too much background knowledge. So in the next step, let me shortly introduce you to Clifford circuits, which are used here in the Tableau representation, and why we're using and focusing on Clifford circuits. Clifford circuits basically are a subgroup of circuits which consist solely of Clifford gates, which the name might already suggest. The Clifford group, let's call it Cliff N, is precisely those group of operators which map Pauli products onto Pauli products. Here you can see, for instance, the operator U and the product of the application of an operator U on a Pauli product will itself be a Pauli product again, which is the definition of a Pauli group. And maybe some more intuitive examples, as some of you might already have seen, are the Hadamard gate and the phase gate, which are single qubit gates, or the already used CNOT gate, which I used on the last slide with the point and cross notation. One aspect of Clifford circuits, which is both an advantage and a disadvantage, is that it can be simulated classically according to the Gottes-McNill theorem. In this instance, it might look trivial since it's already classically simulatable. However, there are also applications where Clifford circuits become beneficial, for example, in quantum error correction, which is very important as soon as we leave the NISQ era, the noisy intermediate state quantum device era, and come to actual quantum computers with error correction. And one other aspect is that even though you might have algorithms to be compiled on a hardware that are not yet only Clifford, you will still have subparts of your circuit that will be Clifford, which can then again be optimized using such a method. And one other big advantage of Clifford circuits is that it can be entirely represented using so-called stabilizer tableaus. And therefore, the entire operation of your circuit acting on the qubits can be encoded in just a single tableau. If you would like to know more about Tableau representations, I put some reference in here, which really explains it well. Yet I will give you a brief overview on what it is so you can better understand how our program works and what you can and cannot do yet with it. The Tableau representation of Clifford circuits looks basically rather simple. You have this type of tableau only consisting of Boolean variables. Here, n is the number of qubits of your quantum hardware or the algorithm. In the best case, those will match. And the size of this matrix is n times 2n plus 1. And this encodes the entire information of your algorithm that you would like to execute. However, this is just a very condensed version of a larger formula, so-called generators GI, which encode any output quantum state of a Clifford circuit. In principle, to condense this in a nutshell, the generators, the entire set of generators, will all have an eigenvalue of 1 when applied to the state that your quantum algorithm would produce. So therefore, the state stabilized by all those generators is uniquely specified, and there will be no other state possible when taking the entire set of generators. And this generator has this rather generic form. And one row of your tableau encodes one of those generators, and the entire set of which will then give you the specific set that encodes and uniquely determines your state of your algorithm. In principle, you can have here your Pauli X submatrices of all your qubits and your Z contributions. And for example, if you have a Pauli string within your stabilizer, your generator, which has an X on the first Pauli product multiplier and an X on the first Pauli multiplier, you would have a power and an exponent of 1 in this instance and a 0 here, since X, the Pauli operator X to the power of 1 is the Pauli X operator, and this would just become the identity. If you would have a Z operator as your Pauli product multiplier, you would have a power of 1 here and a 0 here. If you had an identity for your Pauli multiplier, you would have a 0 in both instances. And in case you would like to encode a Y operator of your Pauli matrices, of your Pauli operators, you would have a 1 in both instances, since in principle x times z is y. However, you would still have to include an additional imaginary contribution, since x times z is I times y. And you would therefore have to keep track of all the additional i's in terms of this I to the power of ri at the end, which just sums up the products of your exponents. And in case both are 1, therefore encoding an additional y, you would add 1 I in your face here at the end. So in principle, this tableau consisting only of zeros and ones will encode your entire circuit that you would like to represent, and that you can then work on in different kind of matter within the code. Therefore, we abstract the gate-based circuit for a moment into a Boolean representation of the state that is encoded by your algorithm, which already leads us to the next slide. Since this is then combined by our side with a Boolean satisfiability problem, which I will give you a very brief introduction to now. So in principle, Boolean satisfiability problems try to solve a Boolean formula. What is a Boolean formula? For a very abstract and simple example here, I gave you an excerpt of such a Boolean formula. Herein, which is shown in terms of a so-called conjunctive normal form, you have so-called clauses. Those are the brackets shown here. And within the brackets, there are, in principle, arbitrarily many literals. And all those literals, being Boolean variables, can either evaluate to false or to true, and you also have some kind of negations here at the beginning. So for example, if you would like this expression to evaluate to true, the variable xi t plus 1 would have to be false, so 0, to be after negation evaluated as true. And for conjunctive normal form to be fulfilled and therefore satisfiable, at least one of those literals within such a clause has to evaluate to true for the clause to be evaluable to true. So at least one expression must hold true within such a clause. And if you would like to be the entire formula to be satisfiable, all the clauses have to evaluate to true for the formula to be satisfiable and therefore for a solution to exist. How this comes in handy for our problem will be explained by me in a minute. Advantages of such formulation are that this type of problem is already widely applicable in other instances. For example, the classical counterpart of quantum compilation, there is the so-called electronic design automation of classical processing units. And this is widely used there, but not only in that instance, but in many more. So since so many people already work with this type of formulas, it's already quite standardized and very well known, which leads me to the advantage that there are already many such solvers available who you can feed those formulas to. They will solve them for you and tell you not only that there is a solution, but also give you the actual variable assignment, which variable is true, which is false, back, so that you can then work with those solutions in terms of your routing procedure. And those such solvers are also competing annually against each other and solving problems, and there is still some progress there that they even try to improve such solvers. Disadvantages, however, for such a Boolean satisfiability encoding is that the efficient encoding is in itself an art. And as already mentioned, the better you encode your problem, the more the speedier your compilation will be. And you can have a better encoding running faster and a worse encoding taking longer for your compilation and the routing procedure of your circuit. And one other disadvantage here is that such problems are generally NP-complete. Yet the advantages overcome the disadvantages here, which is why you're working with the satisfiability approach. So let me give you a basic run on how this is done within our program. This is so-called, our program is Qronos. It's a Python program where Qronos stands for Quantum Routing and Optimization Software. And circuit optimization in Qronos is done in the following steps. So first of all, and I won't go into detail how this is done precisely, but the first step is that you take your input circuit and make out of this the associated stabilizer tableau that is then used in the following program, which will be the final state of your quantum calculation. And which is the endpoint of your quantum calculation. You would, of course, also need a starting point. So you also have to define an initial state and its tableau, which in principle can be any type of tableau, yet it's most feasible to stick to the all-zero tableau, which represents a state where all the qubits of your quantum processor are initiated with zeros as their value. What you then do, and this is now the more complicated part, is that you have to connect both tableaus and set up intermediate tableaus and connect them through those subclauses. You can imagine each intermediate tableau to be some kind of snapshot of your calculation, where each succeeding tableau is equivalent to your previous tableau, but has one gate applied more. So let's take the initial state and its tableau. The intermediate tableau after that will be the tableau that has one gate applied on your initial tableau. The tableau thereafter will have an additional tableau gate applied in its encoding, and setting up a certain number of tableaus and having the final tableau at the end will allow for a connection between your initialization and your final circuit that is encoded in your tableau with a predetermined number of tableaus in between, and connecting them through clauses which actually encode gates. So different clauses will allow for different gates connecting those tableaus. And if you now set up a line of, let's assume, 9 intermediate tableaus, so 10 steps going from one tableau to the next, a satisfiability solver will tell you, is there a solution connecting the initialization with the final tableau using only 10 time steps, since it is capable of using all the gates in between due to your encoding of the gates via subclauses. And if there is no such solution, it will also tell you there is no solution, and you can then assuredly know that there will be no circuit that encodes your circuit, your initial circuit on the quantum hardware using only 10 gates. And you therefore apply the SAT solvers. And what you now have to do is to combine this with a binary search with the number of tableaus as the variable. So for instance, if there is here no solution using 10 time gates or 10 time steps with in total then 11 tableaus, you would double the number of tableaus, for instance, that you in total have 20 time steps. And if you find a solution for 20 time steps, but no for 10, you can iteratively halve the interval of your possible solutions to eventually converge at the precise number of gates still representing your quantum circuit on that quantum hardware, where you know there will be no circuit that uses one gate less than the one that is found. And the main challenge here is to create an efficient SAT encoding of this problem. But maybe I have talked enough in this regard. Let me show you some live demonstration of the program and how this may look like. This is the current version of Qronos. There is not yet a fancy input file, how you can always set up your files. At the moment, you have to do this at the head of the main file, which is not elegant, but I know. But at the end, this still works, and it's only so few people working on this project, so we have to improve this somewhere later on. But for now, there is a section which is editable by the user. And you can set up here, first of all, your input file. That is the circuit that you would like to compile. You do not necessarily have to route your circuit. You can, in principle, also just optimize your circuit, which is done by not providing any hardware restrictions. So if you set this hardware restriction to false, it will just optimize your circuit regardless of any hardware. But however, if you would like to take a routing procedure, you can, of course, also provide some type of edge list. What I prepared here for the demonstration, since we are mainly interested in routing, is this very plain circuit in our yet own format, consisting of 4 qubits and 11 gates. And this has 11 CNOT gates. So since routing only affects multi-qubit gates, this example shall demonstrate how routing is working. But however, you could also in principle add additional single qubit gates and it would still work. But for the demonstration here, I just focused on CNOT gates, which here, for example, have a CNOT between 3 and 0, some others between 0 and 2. So there are also some multi-qubit gates which are not directly connected if you had a linear quantum computer, which is defined here in the edge list. The edge list can be directed or undirected. Here, qubits 0 and 1, 1 and 2, 2 and 3, and 3 and 4 are connected, but there are no any other connections. So there are 5 qubits in total, which have this linear connection. You would not need 5 for 4-qubit instance here, but in principle, this still works. So I could also just reduce this to that. And yeah, if you would then also have to some kind of clever LaTeX output, you can also let your circuit be rendered in LaTeX code so that you can just copy paste your compiled circuit and put it into LaTeX and it will render you a nice picture. And of course, the final circuit itself will also be stored. The input circuit can, for a moment, be our own plain format, but also some type of reverse engineered OpenQASM format. We are still working on this one since there are so many features that can be in there, but for the moment we are focusing on making it run. And to now get to the more advanced section, you can specify and should specify which type of Clifford gates shall be used within the output circuit. So if the program now knows there is a CNOT gate, there is a Hadamard gate, there is a phase gate, and an identity possible, it will only try to compile your circuit using the gates that you specify here. I did not, for example, now here specify an X, Y, or Z gate or a control Z gate, which would not be needed for our demonstration here. So if you already know that there are some types of gates not required for your compilation, you can directly exclude those, therefore speeding up the compilation itself by reducing the search space of the algorithm. But you may also like to reduce the type of gates if you already know that certain type of gates might not be applicable on your quantum hardware that this circuit is designed for. And you could also, in principle, change the SAT solver that is used to solve the formula. For the moment, there is about 1,000 different solvers accessible in Qronos. There are different target metrics, what your circuit shall be optimized for. For now, I was mentioning only the gate minimal solution, so that circuit that has the least number of gates. However, since some gates can also be executed in parallel, you could try to focus on the depth minimal solution. This is not yet implemented, but will be implemented somewhere in the future. And there are also some other features that can be changed if you're a bit more familiar with satisfiability solving. But enough of talking. Let's maybe just let this run. So run the circuit that we just had. And let me explain you how the binary search and the output are working. So what the program will do at the very beginning is to show you all the inputs that you specified. If you provide an edge list, it will also tell you what the edge list look like. It will tell you which gates you were allowing within the optimization, some parameters of your satisfiability solver, and some initial variables like the qubit count or the initial gate count or the number of variables and clauses that are used at the beginning of your satisfiability search. And as you can already see here, we had 11 gates in our circuit to be optimized. So we already know, since we do not have routing in there, that the worst solution possible would be the one with 11 gates. So we do not have to check solutions with 12 or more gates, since we already know 11 gates will be the maximum number of qubits, the maximum number of gates for this type of circuit. And the binary search as a lower bound with at least one gate will then start at the middle with just 6. And apparently it does find a solution which only uses 6 gates. So it reduces the interval that we are searching for from 1 to 11 to 1 to 6 gates. Then it will check the middle and try to find a solution using only 3 gates. So that there are additional 2 tableaus, so 3 steps between tableaus. And apparently it does not find a solution using only 3 gates. So it changes the interval from 4 to 6. Being from 4 to 6. It will then try to find a solution for 5 gates. Apparently, there is a solution using only 5 gates. And since there is no solution for 3, but a solution for 5, it still has to check whether there's a solution only using 4 gates. And apparently there is no. So it can finally shortly say that the least number of gates required to execute this quantum circuit is 5 gates. And it will also do some sanity check at the end and give you your circuit, not only here in the output, but also in terms of a file. And you can see here that this is the optimized circuit of the input circuit. And here is in principle also your copy-paste LaTeX code. Since we are interested precisely in routing, I would now also like to do this, but with the hardware restraints that I just mentioned. So now only the linear connection of qubits is allowed that is provided in terms of this edge list. So let's run this again. And here you can see a slight drawback, since we already know that the performance of Qronos is not yet optimal, but I will get to this in a bit more detail on my last slide that I prepared. But for this technical part here now, you still have your input circuit, and now with hardware connectivity and restraints in there. And since we do not know yet what the upper bound for our compilation will be, since 11 input gates do not necessarily have to be less than 11 output gates, there is not yet a direct binary search at the beginning. But what it does is still trying to find a solution which uses only 11 gates. And apparently there's no solution. And what it does then is to increase the interval by a factor of 2. So it sets the upper bound to 22 and the lower bound to 12, since 11 is no solution. Apparently it does find a solution that uses 22 gates. So it will then reset the interval, but then use the middle and start the binary search, trying to find a solution with 17 gates. Apparently there is one. And after succeedingly minimize the interval. And this is in principle the worst case, since 11 was the first number and 12 is the actual solution. So it has to check for all the instances of 14, 13, and 12, whether there's a solution. But in principle, then it still converges quite fast for our instances. And it will then also give you the output circuit, which consists of 12 gates. So in principle, only one additional gate. Yet, as you can see here, and the linear connectivity having those in mind, you can see that all the multi-qubit gates that are used here only use those only those adjacently connected qubits and still encode the exact same algorithm of your input. And then, of course, you also have the final circuit. And now let me switch back to my last slide of my presentation. So I would like to conclude my talk with what I was trying to show you here. We are using a satisfiability-based approach to route and optimize quantum circuits on both restricted and unrestricted hardware. And we had flexible gate sets with arbitrary combinations of Clifford gates, which can come in handy if you already know that certain gates are either not supported or not yet needed. In terms of the performance, what I just mentioned, we have included a symmetry breaker for an improved performance, which essentially tries to reduce the search space for your algorithm in terms of that commuting gates, which would in principle be both valid solutions, are excluded, and there may only be one certain ordering of gates in case that gates commute. This is precisely important if there is no solution for your actual number of gates that you're checking, since it does only have to check one of those, but not both. And if you have many combinations that all commute, this significantly speeds up the solution finding if there is no solution, which is the hardest case here. I tried to make the program output user-friendly. I hope you could follow me there, but I also tried to make the README and the documentation as user-friendly and help new users get going. And the vision of Qronos shall be to eventually, as already hinted in between, to have a strategy for combinations of various approaches, so that this can become some kind of toolbox which not only has a satisfiability approach for Clifford circuits, but also maybe some T-gate heuristic, which can then be used alternatingly. And if you then also include some kind of smart automation, which already can get a guess from the input circuit which section of your quantum circuit can be optimized best with which module, this would be my future vision or our future vision for this program. And the next steps that would be for Qronos would be publishing its entirety in a paper, which we are already working on right now, and of course making Qronos accessible to others as soon as the paper comes out. And thank you for the kind attention, and with this I'm open for any questions.